Okay, so let's welcome Professor G for his second lecture.
Okay. Yeah, same group of people. So now let's add more flavor to it, right? The crystalline form is already pretty interesting, but by introducing the Moray superlattice, we got things that's very differently and very interesting. And this will include a lot of new progresses that we're still trying to understand. I'm not sure if it makes the case more clear or it brings more mystery, but I will just show you. Okay, so now we change topic, right? We change to fractional quantum Hall effect, which is really a beautiful example to show how topology and correlation can work together to give you something really amazing. And Princeton, again, is a special place to talk about this because of efforts by Dan Cui, Mansour, and Lauren Pfeiffer on this gallium arsenide topic. So basically, not only you can have integer quantum Hall effect, which is a single particle effect, you can also borrow the interactions between electrons and open up gap at the fractional fitting of lambda levels, right? And then you measure quantize the Rxy at h over e squared divided by the corresponding fractional fitting number. And this happens in extremely clean two-dimensional electron gas. In gallium arsenide system, it happens at a high magnetic field. And once you have such kind of fractional quantum Hall ground state, it leads to charge fractionalization, fractional statistics, composite fermions, many beautiful physics emerging from this combination of topology and the correlation. Just like people were thinking about how to realize integer quantum Hall effect without magnetic field, there were also thoughts about how to realize fractional quantum Hall effect without a magnetic field. Okay, and there were a series of works back in like 2011. Without talking about any specific materials, theorists were just thinking about, is this possible at all? To realize a fractional Chern insulator. And in principle, the fractional Chern insulator should give you a fractional quantum anomalous Hall effect at the zero magnetic field. They were thinking about, okay, is this possible? What does it take to make such kind of state or effect? And my view on what they conclude is that you should just mimic lambda levels, okay? Because lambda level give you the fractional physics. Let's try to mimic lambda levels without using magnetic field. For example, lambda levels are very flat to promote electron interaction. So you want to find some crystal that has flat band, okay? And lambda levels have topology in them. Each lambda level have a Chern number equals 1. So you want to have your band not only being flat, but also topological. And lambda levels are well separated from other lambda levels. So when you partially fill the one at the Fermi surface, you don't worry about the perturbation from the other bands. And in the crystal case, you don't have that well-defined cyclotron energy, but you have this thing called the exchange interaction, which could generate a gap between two bands that are, for example, time reversal pair of each other. And then maybe, if you're lucky enough, you get fractional quantum Hall at the zero magnetic field. Right? Again, this is borrowing the barrier curvature as an internal sort of magnetism thing. Of course, this doesn't tell you exactly what material to look for such kind of state. And I'm trying to tell you that Moray superlattice of 2D material is the place or one of the place to look for it for the following reasons. Okay, because we talk about the the k to the nth dispersion. Let's just start from that and see how you can mimic lambda levels in this platform. You have this band dispersion here. Part of it is somewhat flat, especially if you go to high layer number, like for 5 layers. But it's connected to the more dispersive part, right? Does this look like a lambda level? No, it doesn't. The first thing you can do is to put it on a Moray superlattice, right? Between, for example, graphene and HBN. You get a Moiré period on the order of 10 nanometers, and you can open up a gap at the boundary of the mini Brown zone defined by the Moiré period, right? Momentum is 1 over the Moiré period. And the Moiré potential is going to open up a gap at this boundary and sort of cut out some of the dispersive part of your band, right? Trim it so you are only, you can only, you only worry about what happens at this relatively more flat part at the 0 energy, okay? But still, this doesn't look like a lambda level. The additional thing you can do is to play with this gate electric field thing to open up the band gap, so you can separate these blue band and the yellow band, and eventually you can get something like this that I call flat band. Does this look like a topological flat band, or does this look like a lambda level? Somewhat, right? It's not perfectly flat, but it's pretty flat, a few millieV, 10 millieV bandwidth. And is this topological? I hope I've convinced you through the first talk. There are a lot of barrier curvatures near the band edge. So these states in this flat band should also have barrier curvatures that can make it topological. And the third thing is this band isolated from other bands? Yes, thanks to Moiré, right? So another way of thinking about why mimicking lambda level is easier to do in Moiré superlattice than in atomic crystal is if you think about the number of charges you need to control. Okay, if in a crystal, you have many charges because you want to make the whole Brown zone flat, and we know that's hard. Although there are examples of materials like Kagami systems that give you flat bands, in a big range, but in general that's hard. Well, in Moiré, you have a much easier job to do because Moiré is much bigger in real space than the atomic bond length, which translates into a much smaller volume in the momentum space. And that corresponds to a much smaller number of charges you need to include in your flat band, right? In other words, you don't have to have the whole Brown zone to be flat topological band. You just need to cut out the flat part of a generally very complicated dispersion. And that is enough to mimic lambda levels. Okay, that's why this fractional quantum anomalous Hall is experimentally first discovered in Moiré materials. So that's a general idea. And again, we're going to build upon this 5-layer rhombohedral graphene. We're going to introduce a Moiré superlattice between the top HBN and the topmost layer of graphene with in this specific device is about 12 nanometer in length, correspond to a twist angle of 0.7 degree. I want to emphasize that this period is mostly set by the lattice mismatch. If you're at the perfectly 0 degree, the Moiré is going to have a period of about 14 nanometer between graphene and HBN due to the lattice mismatch. A small twist angle of 0.7 degree changes that a little bit, but not much. And we apply the same, the tuning knobs, right? We can control the charge density and control the displacement field. And as I told you, when you open up the band gap, you can squeeze the bottom of the conduction band and make it even more flat than at d equals 0. And this region, this phase diagram corresponds to putting electrons in this conduction band bottom here, okay? You have two choices. You can apply the gate electric field upward or downward, and the effect is whether you push these electrons in the flat band here to close to the Moiré or far away from the Moiré, right? Those are the two limits, and as you can see, when you push the electrons right next to the Moiré, you get some insulating states here at the integer fittings of the Moiré superlattice. Mu is an integer, is a fitting factor, right? 1, 2, 3, 4. Every time you hit an integer fitting, you get an insulating state that is topologically trivial. And this is similar to what happens in other Moiré superlattices where the Moiré potential is strong. For example, twisted bilayer graphene, twisted TMD. But there's no topology here. And if you change the sign of your displacement field, you're polarizing your electrons to the layer that's away from the Moiré. First of all, you don't really see those insulating states. And the integer fitting, that tells you the Moiré potential is much weaker than than this side, but it's still not topological yet, right? There's no like vanishing RXX. Well, it turns out you have to go to much higher displacement field than I was showing you. You kick it to something like 1 volt per nanometer in terms of the displacement field, and suddenly there's a striped region in a tilted fashion that has something going on in both the longitudinal resistance and the transverse resistance maps. Okay, the longitudinal resistance shows a big region that is continuous and very insulating. This is really like hundreds of megohm if you go to low enough temperature. And we think, okay, maybe this is a weakened crystal, maybe it's under localization. There's no easy way for us to differentiate now, but it's part of the flat band physics, right? And the upper half of this tilted region, which I circled here, has a lot of anomalous Hall signals. Okay, this is already anti-symmetrized, so you don't need to worry about the geometric influence of the device configuration. And you see there are vertical stripe features at fitting factor 1, 2/3, 3/5, 2/5. Some of them are easier to see in the RX Y map, some of them easier to see in the XX map as dips. So this corresponds to fitting 1 Moiré flat band of the same spin and valley polarization. That is how the temperature symmetry is spontaneously broken and the system becomes an orbital magnet by itself. So let's first look at the integer one, right? The fitting factor 1 here, the RxY got quantized at h/e². So this is a Chern number equals 1 integer quantum anomalous Hall state. It makes sense. It doesn't make sense, to some extent. It makes sense because most of the integer quantum anomalous Hall people have seen has Chern number equals 1. This is another one. What doesn't really make sense in the naive picture is I was telling you the pentalayer graphene in principle can host the C equals 5. If you harvest all the barrier curvature, it's C equals 5. And this is a fraction of that. And it's not exactly clear why it is 1. But anyway, it is a C equals 1 state. The RxY is quantized as well. RxX go to 0 within like a few ohm fluctuation level. So it's very well defined. And this perfect quantization can persist to almost 2 Kelvin in temperature. Okay. So there's no question about this part. This is the really important figure. This shows the fractional states. Okay. The RxY has plateaus at 2/5, 3/7, and a total of 6 fractional states. 3 of them are below half filling. 3 of them are above half filling of the Moiré band, and they all fall into the so-called Jane sequence with all even denominators here. And the perfect quantization of this fractional state, for example, in the 4-9 state, can persist to about 400 millikelvin or higher. So this is the fractional quantum anomalous Hall effect. This is happening at 0 megafield. And there are also hints for composite Fermi liquid at half filling. You see, at half filling, there's no gap. Okay, there's no dip in RxX. There's no local plateau in RxY, so it's not gap there. But the value of RxY is 2h/e², which is basically h/e² divided by 1/2, right, as other fractions. And the RxY varies linearly in the neighborhood of half filling. So this really looks like the composite Fermi liquid in the fractional quantum Hall case. Although we don't have direct evidence of a Fermi surface here, which is beyond this simple measurement. And I want to remind you of one thing that I'll come back later. You see there are 6 fractional states here, right? And 5 of them look similar to each other in the sense that RxY is a local plateau on a continuous like tilted line background. So basically, as you go down this tilted line, you stop at somewhere and form a plateau before you further go down. So the RxY is higher at the lower fitting factor side and smaller than the plateau value on the right-hand side. All these 5 states are like that, except for 2/3. 2/3 has Rxy lower than the plateau value on both sides of this little plateau. I will get back to this later. Okay, it feels like this one is somewhat special. It has some competing states nearby. And this is the so-called Landau fan. I'm not sure if you can see the dashed line clearly, but basically what I'm trying to show you is this is the 3 fractions below half filling. These are the 3 fractions above half filling. This is Rxx, so you should look at dips in Rxx. And if you apply magnetic field, all these 6 fractional states will disperse as a function magnetic field according to the strata formula determined by the corresponding fractions. Okay, so this is another way of checking that these are FCI state. Although with the quantization in Rxy, you really don't need this, but this is a self-consistency check. And now I want to talk about something that doesn't make sense. Okay, although I told you in the Ramanujan system, you introduce Moiré, you have a chance to get some flat band that mimics the lambda level, so you get fractions. Okay, but in reality, it doesn't really work that way. And this recipe of getting fractional quantum anomalous Hall in Ramanujan graphene HBM Moiré was not proposed by anybody before the experiment. There were theory prediction of fractional quantum anomalous Hall effect and fractional Schrödinger insulators in twisted TMD and in twisted graphene or strained graphene. And now you know that in twisted TMD, twisted MOT2, it worked out, right? There's twisted MOT2 by Xiaodong Xu's group. They observe fractionally quantized Rxy for 2/3 and 3/5. And there are also signatures in the optical measurement and thermodynamic measurement to support that FCI there. And in the twisted graphene case, so far the best result is what Emil Jacobi at Harvard got. They observe FCI state persists to something like 5 or 6 Tesla. It's not 0. It's still quite big field. And nobody was predicting fractional quantum anomalous Hall effect in rhombohedral graphene HBM. And later, we thought about why that's the case, right? And then this is what we realized, also pointed out by the theorists. So you have a very flat band bottom here, okay? And it can host a lot of charges. Even if you just consider one species of isospin, right? Spin and value polarized, 1/4 of the whole band structure. And you ask the charge density that we observe this fractional and integer quantum anomalous Hall effect, how much area does it occupy in this flat bottom of the band? And the answer is the Moiré is enough to include this much electrons, okay? It's enough to include this much electrons for filling factor 1, which means you have a lot of other electron state that's at the close neighborhood in energy. And if you apply the scheme of folding your band into the mini boron zone defined by Moiré, in the weak Moiré potential limit, you are not going to get isolated bands like lambda levels. You're going to get several bands that's all entangled together. So at least at the single particle level, it doesn't look like a lambda level. And the second thing, which maybe the first thing is how do these electrons even feel the Moiré? Because as I said, this effect happens when you polarize the electrons in the flat band to the layer that's away from the Moiré, right? 1, 2, 3, 4, 5 layers. Layer 1 is next to the Moiré. Layer 5 is away from the Moiré. So there's almost no tunneling from electrons in graphene to HBM tunnel back and get Moiré potential that way. So what does the Moiré do here, and how does Moiré influence things, and why would the electrons, even being far away from a Moiré, knows what density corresponds to Moiré filling factor 1? Okay, that's not clear even now as we're speaking. So after the experiment observation, there are a lot of discussions by theorists, different groups did different calculations, and there's still no consensus on exactly how this happens in this particular material system. And that's probably why this was not predicted by theory in the first place. And then I also want to compare this system with the twisted MOT2. You'll probably hear from Xiaodong tomorrow, the fractional quantum Ohm's Hall effect in twisted MOT2. They look very different in the setting, okay? Although they both share 2/3 and 3/5 fractional state. But MOT2 is a semiconductor TMD that has very strong spin-off coupling, while graphene has almost no spin-off coupling. And MOT2, twisted MOT2 forms this spatial pattern of the pseudospin, which is basically a layer degree of freedom, right? So it forms this skyrmion patterns of the pseudospin in real space, and that somewhat, looks like an immersion magnetic field through the spin-off coupling. And this theory by Alan McDonald actually happens before the experiment in twisted MOT2, and they think that's important for getting this fractional quantum Ohm's Hall effect, or FCI. Well, now the question is like, how can a system like graphene has almost no spin-off coupling and no like layer pseudospin skyrmions, no immersion magnetic field, deliver the same effect as twisted MOT2 give you? So maybe it's valid to ask like, what do you really need to get this state, right? Maybe the recipe is more general than we used to think. Okay, so that's what we have published already, and it's a small fraction of my session 2. So there are a lot of new progress I will share with you. I name 1, 2, 3. Okay, let's go one by one. Number 1 is quantum Ohm's Hall and the fractions in high Chern number band, right? As you know, each Lambda level has the Chern number equals 1. And you know how things get fractionalized in that band. Well, in principle, the Chern number of a topological flat band can be bigger than 1. It can be 2, it can be 3, it can be any integer. And there's indeed high Chern number topological flat band in the rhombohedral graphene HBM array. Okay, so and that they may give you different results from what happens in a C equals 1 band. Theoretically, people realize this high Chern number topological band scenario in rhombohedral graphene HBM array superlattice, even as early as like 2019. Okay, this is Santheo's paper where they're talking about ABC trilayer graphene, because at that point people think trilayer is hard enough to make, so nobody bothers to go beyond trilayer, right? But in trilayer, the simple case is that you can have C equals 3 by harvesting all the Berry curvatures. Well, experimentally find C equals 2, right? Although it's not perfect quantized at 0 magnetic field, but you apply some magnetic field, it got quantized at the C equals 2. This is an experiment done by my advisor Feng Wang at the UC Berkeley. And then there are more calculations of like thicker layers, 4 layers, 5 layers, and they were arguing, okay, on the whole side, this is the whole band, you can have Chern number equals 4 or 5, the same as a layer number. Okay, there are all these possibilities, and if this band is flat enough, maybe you get fractions out of this high Chern number band. So far, experimentally, we did observe high Chern number flat band. Okay, this is a sample that's 4-layer rhombohedral graphene HBM array, and this is the map on the whole doping side. This is RxX, this is RxY. You notice that there are 2 things going on. One is, you get some insulating state at fitting factor 2. Okay, 2 holes per array. It's very insulating, and that's why you cannot have a well-defined measurement of the RxY. It's just fluctuating. It's topologically trivial. However, there are also topological state seams on the map. One is at fitting factor -1. Here, you have a lot of Ohm's Hall signal, and you have a vanishing RxX. And the other is happening at around fitting factor -2.5. You have an Ohm's Hall, which is the opposite color from here, right? Opposite sign, and a dip in RxX, not as vanishing as here, but it's definitely a local minimum there. So this mu equals -1 state turns out to be a high Chern number quantum anomalous Hall state that has RxY quantized at h/4 e² and correspond to a Chern number equals 4. Okay, and the Rx go to 0. So this looks as well defined as the integer I was showing you in the pentalar case on the electron side. And you check the strata formula, the Landau fan in magnetic field, this state dispersed with the right slope correspond to C equals 4. So if we just talk about quantum anomalous Hall effect in Moiré systems, this is the biggest Chern number people have observed so far. Again, everything else is C equals 1. This is C equals 4. And then you can ask, okay, seems the C equals 4 band is flat enough. That's why it can be singled out and break time versus symmetry spontaneously. So can you have fractions in this high Chern number band, right? And remember, there's this thing happening at around filling factor 2.5, which is not integer. And if you check the hysteresis, Rxy seems to be quantized at h over 3 e squared, correspond to a Chern number equals 3 with very small error bar. And Rxx is much smaller than Rxy. So if you only look at this, okay, you may say, oh, this is an integer quantum anomalous Hall state happening at maybe half filling of the third band or the third flavor of the first Moiré band. However, we got some puzzles here by looking at the Landau fan map. You see, this is that state at filling factor around 2.5. But when you apply magnetic field, it disperses with a slope that is much bigger than 3. In principle, these two things should agree with each other if the state is a gap state. But phenomenologically, it feels like in order to stay in this state, every 7 electrons you put in the system as you increase the magnetic field, only 3 of them contribute to the edge transport, and the other 4 or 5 electron is doing nothing. Okay, and but they are injected into the system, so they have to at least form something that like a Wigner crystal, which doesn't contribute to Rxy thing. Yes.
Mu and the C. So in the previous slide, you have a mu to 2 state, which are not dominant. What is this? What their C? What is the Hall conductance in those mu to 2 state?
Oh, that's topology trivial. There's no anomalous Hall. Yeah. Yes. So something is going on in fractional filling of this high Chern number flat band, but we don't fully understand what it is. So there are 3 things, right? Filling factor, the Rxy value, and the strata. So far, none of the 3 agree with each other, which is quite puzzling. I mean, it's okay to have the filling factor and the Chern number do not agree with each other. That is allowed, but this disagreement between the Rxy and the slope in strata is the part that is confusing. Okay, I hope this will become more clear as we do more measurement. Okay, why? And the second new progress I want to share with you is, answering a lot of my confusions previously, like why would the FCI and the fractional quantum anomalous Hall effect happens on the remote Moiré side when the electrons feels very weak, if not some Moiré potential at all? What happens on the strong Moiré potential side? Okay, I was showing you got the insulating state at 1, 2, 3, 4, and that seems to suggest everything is topologically trivial on that side. But it turns out that's not true. So after our transport measurement, we want to understand this fractional state better, which means we want to do more experiment different from in-plane transport. For example, we want to measure the compressibility of this state to show their gap and measure how big the gap size is to better modeling and understanding such kind of effect. So we make samples for our colleague Ray Ashuri at MIT, who is world leading expert on such kind of capacitance measurement. So this is one example. Okay, so this layer in the middle is a bilayer graphene. It's AB stacked bilayer graphene. There's top gate and there's bottom gate voltage. So what they can measure is the so-called penetration capacitance, CP. And how that works is that you apply some AC voltage modulation on your top gate, and you measure the charge get in and out of the bottom gate to tell what's going on in between. Okay, imagine if what you have in the middle is a perfect insulator, then it will not screen the electric field that's penetrating through. So you will have the charges in the bottom layer follows what respond to the gate voltage modulation in the top layer, and you'll measure a big penetration capacitance. Well, if the layer in the middle is a very, very conducting layer, like a metal, then when you modulate the gate voltage on the top gate, the electric field will get screened by the metal. So the electrons in the bottom gate feels nothing. They just don't do anything, right? In that case, you get a small, penetration capacitance. And applying this idea to the AB stacked bilayer graphene, we use gate electric field to open up a gap. The gap is an incompressible state, right? There's, in order to go through the gap, the chemical potential to jump from valence band to conduction band, it takes very little amount of charge. So they did observe a peak in the penetration capacitance and tell you this gap state is incompressible. So we want to apply the same technique to this pentalayer graphene HBN Moiré superlattice system and measure the electron compressibility. So basically, the penetration capacitance is proportional to inverse of the compressibility. And we want to use this tool to provide the information that you cannot obtain from in-plane DC transport, right? You can quantify the gap size, how the chemical potential changes as a function of doping, things like that. And this is what we got, okay? So we don't have a device that mimics the transport device on the weak Moiré potential side, but we do have a device that we can measure very comfortably by pushing the electrons close to the Moiré, okay? So Moiré is here, and we can apply displacement field to push the electron to this close to Moiré side. Again, it's filling some flat band at the bottom of the conduction band, but now these electrons can feel the Moiré potential. And then this is the big map they got. So basically, this is a compressibility map. Bright regions correspond to gapped incompressible state, and relatively dark region correspond to compressible and no gap state. Okay, and what you find is, this is D equals 0. And this is that layer antiferromagnetic state, we think, at the D equals 0. So clearly, it's very bright, it's gapped. And this is the side that corresponds to electrons pushed away to the weak Moiré potential. Unfortunately, this side, you see there are a lot of streaks like this. That's because the electrical contact to the channel in this case is very bad. Even for for the compressibility capacitance measurement here, you cannot measure those fractional states in this region here. It's swamped in some random fluctuation things there. But you can still see that C equals 1 state. This is the C equals 1 state. It is gapped. Okay. And there are more features on this side when you push the electrons towards Moiré, so they can feel strong Moiré potential. And you see gap state at the filling factor 1, 2, 4, not exactly 3, right? But integer fillings. And there seems to be something going on here. And let me zoom in. So this is filling factor 0. This is filling factor 1. And this is filling factor 1/3. This is filling factor 2/3. You have some local maximum of the compressibility, and that tells you got gap here. Okay? And these gaps are trivial. This is a CDW state, or some, there are people calling such kind of state as generalized Wigner crystal state, because it's in a Moiré superlattice, and 1/3 and 2/3 are sort of commensurate with Moiré, that can help stabilize the Wigner crystal. So you get the essentially CDW state at 1/3 and 2/3 at the 0 magnetic field, which is not topological. But when you apply magnetic field you see that, okay, this is a CDW, this is CDW, 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 CDW. At the same time, in this region here that has no feature to begin with, it gradually starts to show something brighter and brighter and brighter. Okay, I guess at 1 Tesla, it's very obvious that there's a bright vertical stripe here. And there's small shifts from this stripe to this stripe here. So they happen not exactly at the same charge density or filling factor. And this position is shifting with magnetic field. This is actually FCI. It shifts with a fractional slope of 1/3 or -1/3. It shifts to the lower density part, okay? And another way of looking at this, coexistence of CDW and FCI and evolution as a function of magnetic field is to, again, to do the Landau-Fan. This is the same plot I was showing you. And now I'm going to cut it in different directions and do Landau-Fan measurement. Okay, I'm going to do 3 cuts. The first cut here cuts through the bottom of this 1/3 CDW state. Okay, as a function of magnetic field, as you can see, this is at 1/3 CDW state. Okay, and it persists to something like 2 Tesla, and then in a vertical way, which means it's topologically trivial, and then it picks up a slope like this, and that is the FCI tracing to filling factor 1/3, and it has a slope of -1/3. That's a green line here. Similarly, there's something at tracing to filling factor 2/3. That is this one. That corresponds to this green line with a slope of -2/3. So there are FCI states on this strong Moiré potential side. Okay, that's a conclusion 1. And then you ask, like, how low a magnetic field can these FCI persist to? Do they go to 0 magnetic field if you cut in the right direction? So that's why we make more cuts, right? Cut 2 is like this way, diagonal way, and cut 3 is here. Cut 3 cuts through the top tip of this 1/3 CDW state. And as you can see, in cut 2, this green line here for the 1/3 FCI goes to smaller magnetic field. And cut 3 is even smaller magnetic field. Okay, if you look carefully, there's almost no CDW here. And the FCI persists to almost 0 magnetic field. Okay, 0.1 Tesla or so. So it's very close to 0. Okay, it's not there at the 0, but it's very close to 0. You just need a tiny magnetic field of 0.1 Tesla. You can induce FCI in this very strong Moiré potential side. And you have to compete with the CDW state, which tends to form in the strong Moiré potential, right? That tends to localize the electrons. Of course, you also have to win the competition with some trivial Fermi liquid things. But anyway, the conclusion is at least this part makes some sense. It's not as bizarre as a weak Moiré potential side. How does the Moiré work thing? This side, there's strong Moiré potential, and there's CDW. There's CDW to FCI transitions. And this is probably similar to what happens in twisted MOT2. And the FCI is in twisted bilayer graphene. Because in both those 2 cases, electron feel strong Moiré potentials, and there are competition between CDW and FCI. Except for in twisted bilayer graphene, again, you need 5 to 6 Tesla magnetic field. Well, here you need 0.1. So it's almost a 0. But because it's not exactly 0, we missed this in our first transport measurement and thought this side is topologically trivial. Yes?
It's a Moiré side. You may feel there's more impurity, but in the other side, there's a less impurity. Can you say something about whether the sample is clean and also clean?
In terms of the twist angle?
Yeah, the twist on all other kind of randomness.
Okay, I don't see why the charge impurity would be different on the 2 sides. Regarding the twist angle inhomogeneity, there must be twist angle inhomogeneity, right, in any Moiré. But the fact that this Moiré is a hetero-bilayer Moiré makes it much more robust against twist angle variation, because the period is mostly set by the lattice mismatch, right? So it's there, but it's probably a much smaller effect than in the homobilayer TMD or graphene. Yeah. Okay, so this makes this system quite interesting, right? I mean, we have 5-layer graphene on HBN, and these two devices are almost the same twist angle. Actually, we have two devices here on the weak Morris side, two devices here on the strong Morris side. They show consistent behaviors among each groups, and you got FCIs on both sides, the two opposite limits. Very strong Morris limit and a very weak Morris limit. And the weird thing is the weak Morris limit give you even more robust FCI versus other states, so it persists to zero magnetic field and shows fractional quantum anomalous Hall effect. But at least this is the missing piece that gives us some confidence that at least this system is not totally impossible to understand, right? We at least understand this part. And of course, you can ask, what can you learn, by comparing these two cases, right? So maybe you can, compare the gap size extracted from the compressibility measurement. So you may be able to figure out, okay, so although you feel a weak Morris potential on this weak side, but how weak is that? Maybe we can get more quantitative by this comparison in the same system, but different polarity of the gate voltage. Okay, so this is a new progress. And we made the sample, Ray and his student Sam did the measurement. They are wrapping it up. So I would expect this to be posted soon. But I don't control that. Okay. Okay, now let me show you what I do control. This is new progress 3, I call. At the lower electronic temperature, okay? As I told you, those fractional states we observed last year shows perfect quantization already at the level of 400 millikelvin. And the issue then is we have no idea of exactly what the real electronic temperature in the sample is. We read 400 millikelvin from the fridge. For the experimentalists, you may know that there could be a difference between what you read and what the electrons truly feels in temperature. So we spend a lot of time to engineer the temperature, okay? This is what's published last year. You see this nice plateaus and things and dips in RxX, but RxX doesn't go to 0, right? It's on the order of like, 0.5, 0.4 h/e squared. It's pretty big residue. And now we can access electronic temperature about 40 millikelvin through filtering of the lines, because that's important for the graphene devices where electron photon coupling is weak. And as you can see, this is the same device, just to measure again at the base temperature this is not base temperature, but 300, 200, 100 millikelvin. As you can see, this dips in the fractional state, the 5 fractional state I was showing you, the dips get deeper, okay? Every dips get deeper. And because this dip becomes sharper, we now can identify more fractional state, like 5/11 and 5/9 can be seen as the dips in RxX. So it does move in the right direction. The lower the temperature, that gap state give you smaller residue in RxX, although it's still not 0. Now in this device, the residue is about 0.2 h/e squared, which translates to about 5 kilo ohm in resistance. If you're familiar with the fractional quantum Hall literature, this is still huge residue. But we're making some progress, okay? And in addition to the 2 5-layer graphene shows a fractional quantum anomalous Hall, we have that tetralayer device I was showing you on the whole side, right? That tetralayer device also show fractional quantum anomalous Hall effect on the electron band. This is the electron side. You see, this is the integer, being factor 1, Chern number equals 1. And there are 3/5 and 2/3, both as plateaus in RxY and dips in RxX, okay? The interesting thing is that this tetralayer sample at the 2/3 state shows a residue of 0.1 h/e squared, which is even smaller than the smallest dip in the pentalayer device, okay? So this is about 2.5 kilo. So I would say it's still not clear that whether this residue is due to not perfect sample, and we just need to make it better and better, higher and higher mobility, like the gallium arsenide people did in the past decades. Well, we are in year 2, right? Maybe we just work harder and it will eventually go to 0. Or maybe there's some fundamental reasons that it doesn't go to 0. Okay. But anyway, fractional quantum anomalous Hall effect has been observed by us in 2 pentalayer graphene devices and 1 tetralayer graphene devices. They share 3/5 and 2/3 at least. Okay, next I'm going to show you something that's really puzzling us. Okay, you see, I'm showing you 6 fractions here up to 2/3, and I already point to you why 2/3 looks, how 2/3 looks differently from other fractions. Well, here I'm showing 5 out of the 6 without showing 2/3. And the reason is at the base temperature, you don't have 2/3. This is a map we published last year, and I was showing you in my previous section. And this is a big map showing you the 6 fractions, including 2/3 and integer. Okay, it's cut in kind of a tilted fashion like this. This is what you get at the lowest electronic temperature that we have now. Where's 2/3? Okay, 2/3 is supposed to be here. But you almost couldn't tell that apart from the surrounding. The surrounding area shows RXX vanishes. And in the RXY map, again, you cannot tell where 2/3 is, but it's supposed to be here. It shows a uniform color here as anomalous Hall that was not uniform at higher temperature. Okay. And now there are 3 regions. Actually, if you look at the color carefully, this color here corresponds to RXY equals h/e². Not fractional value, it's an integer value. And now there are 3 regions that shows quantization of RXY at h/e². Number 1 region is this little diamond here that is at filling factor 1/2 exactly. Okay, it's broader than just 1/2, but it's at 1/2. The second region is this big region here, shows vanishing uniform blue color RXX and quantize the RXY at h/e². And the number 3 region is the original, sort of inheriting the original C=1 Chern insulator, but now become wider. Okay, there are 3 regions shows h/e², quantize the RXY at the 0 magnetic field, and the 3 regions almost connect into one big regions. So if you do a line cut along this dashed line here, at this specific displacement field, you are going to get RXY of h/e² almost across the board, from filling factor 1/2 to filling factor 1 in this device. Yeah, there are small gaps, right? You can see even here, there's some small gap between region 2 and region 3, and maybe a small gap between region 1 and region 2. But those gaps are vanishing as you cool down, right? If I have one more data point at slightly lower temperature, I would predict this blue line will become completely flat, running from 1/2 to 1. And the fractions, 2/3, 3/5, others, they used to be at the right value of fractional quantum anomalous Hall effect. Now they become integer. Okay. Of course, not the, 2/3 is a special one that is completely gone on this map. Well, 3/5 and 4/7, they are not completely gone. They are partially gone, right? This region, they are gone. But at the lower displacement field, you still see the dips correspond to those fractions. I will show that more later. But anyway, so there seems to be something at the even lower temperature, at least for the part of the phase diagram I'm showing you here. The integer is the ultimate destiny, while the fractions are not. And this, this h/e² has very well-defined magnetic hysteresis loop. It quantizes at the h/e² as you scan magnetic field. Okay, this is a diamond. This is a big region surrounding 2/3. They both show h/e² as you sweep magnetic field. So there are phenomenologically quantum anomalous Hall effect with integer Chern number 1. Okay, but I would argue they are very different from the C=1 Chern insulator, And one way to look at that is, you can do something like this, okay? Oh, sorry about this. Instead of measuring at different temperature, another thing you can do is to park at the base temperature and apply a combination of DC background current and the AC modulation current. You can measure the differential resistance corresponding to that AC modulation current at the different background DC current, okay? At the lowest DC current 0, you got the blue line as I was showing you, right? It's the same thing. But as you increase the DC current more and more and more and more, eventually at like a couple of nanoamp or 3 nanoamp, it recovers pretty much the shape that I was showing you at higher temperature, like 400 millikelvin. Okay, both Rxx and Rxy recovers that fractional quantum Hall liquid behavior at high DC current. Okay, and it doesn't happen in a monotonic way though. If you look at the Rxx here, right, blue is the smallest DC current, and the red line here, red curve, is the highest DC current. But it doesn't just go monotonically from blue to red. There's some intermediate current that give you this huge spikes in the differential resistance. And to make that more clear, let me park at a specific filling factor, for example, 0.79, which is roughly here, and show you how this differential resistance depends on the DC current that I'm applying. And you got something like this. It's 0 when in this integer quantum Hall state, and it covers to whatever value that quantum Hall liquid give you at high temperature. Well, in the intermediate region, you get a pair of peaks that's really, to me, reminiscent of S-wave superconductor. But this is not S-wave superconductor because there's anomalous Hall. There's anomalous Hall. The anomalous Hall is quantized at integer value at a small current and become whatever value that quantum Hall liquid give you at high temperature. Okay? And this is super fragile. You see, these peaks happen at a critical current of something like 0.5 nanoamp to 1 nanoamp. So very tiny current will already destroy this integer quantum Hall state that looks like a big patches on the phase diagram. So it's a very fragile thing. It's much more fragile than this integer state at the filling factor 1, which looks perfectly quantized, across the whole range of temperature and the current, right? So although they both exhibit integer quantum anomalous Hall effect, but they are very different states from the temperature dependence and the current dependence. And this is not something that you see in only one sample, okay? It shows that's a pentalayer sample. This is a tetralayer sample. The tetralayer sample has slightly different twist angle, so the filling factor 1 here of Moiré corresponds to a smaller charge density, right? In the pentalayer, it corresponds to a density of probably 0.85 thing, while here, Moiré filling factor 1 corresponds to a charge density of 0.6. So what you see here is, again, there's a little diamond at 1/2 filling, and there's a big patch showing H/E² if you use small enough current and go to low enough temperature. And the Rxx is vanishing, right? So phenomenologically, they look very similar, except for now, in the tetralayer device, the patch 2 and patch 3 used to be somewhat disconnected in the pentalayer device, perfect merge into one, probably due to the fact this stripe here is moving to lower charge density due to a different twist angle. But it feels like this is a universal observation of some, we call it extended quantum anomalous Hall state running from filling factor 1/2 to 1 in a pentalayer device, and running from filling factor 1/2 to even 1.3 in the tetralayer device. So maybe what matters is not the filling factor of Moiré, because you can clearly go beyond filling factor 1. Maybe what really matters is the absolute charge density from the data I can show you. Okay. Here's more data to show you the difference between, although this is uniform big range of H/E², but they are very different in their response to current, okay? So these two stars, the dark blue and the light blue stars, are at filling factor 1, okay? And you see, in a range of 50 to 100 nanoamp, you get the quantized RXY at h over e squared. But if you park at these 3 other stars, as shown here at the bottom, you get a very narrow range of current that it is quantized at h over e squared. But very soon, that state is broken down and becomes something different. Okay, and go back to this phase diagram here. If you park at the filling factor 1/2, and you just measure your RXY and RX as a function of displacement field. This is the same device, but you can tune displacement field to cause some in situ tuning you can trust, right? It's the same device. You see, this is a plateau that gives you that composite Fermi liquid-like behavior to h over e squared. At a low enough temperature, there's a plateau at h over e squared. That's the little diamond before you go to some Fermi liquid. And if you park at the filling factor, that's 3/5 and 4/7, what you're going to get is at a low displacement field, you still have the fractional quantum anomalous Hall effect. You still have the right value of RXY corresponding to the fractions. But as you go higher in displacement field and getting into this region, bluish region, it's quantized at h over e squared, both cases. So there is some competition between this fractional Chern insulator and this integer extended quantum anomalous Hall effect. That competition depends on the displacement field you apply, depends on the filling factor, depending on the temperature, and depending on the current. Okay, and at the lowest temperature, we can access now this integer state seems to be winning in a big region. Well, you still have this region here that has plenty of fractions. Especially the 3 fractions or the 4 fractions below half filling seems to be doing fine. Okay, they're not eaten by the integer state. But we don't know what will happen if we keep cooling the sample to even lower temperature. Of course, I do not know how to cool graphene more than to lower than 40 millikelvin. I wish somebody can tell me, but that is a front that we're still working on. Okay, and then the question is, what is this? What is this integer quantized state at the lowest temperature that even replace some of the FCI states, right? And comparing to the literature of fractional quantum Hall, that's our source of wisdom, there is something that looks somewhat similar. That's called the reentrant integer quantum Hall effect, which is saying if you park at some filling factor between those fractional filling factors that give you the fractional quantum Hall state, and if you keep cooling it, eventually it will become some integer quantized Hall state. Okay, it goes to the closest neighboring integer, either 3 or 2, depending on which side it is closer to. So that is called a reentrant quantum Hall. Reentrant means as a function of magnetic field, I guess. But there's also a difference between what reentrant quantum Hall is and what we are observing here, because in reentrant quantum Hall, if you park at the fractional filling and you keep cooling it down, fractions are still fractions. Fractions never become integer in the quantum Hall case. Well, in our case, clearly, some fractions can be replaced by the integer. Okay, that's a very different observation. And of course, okay, so what what the reentrant quantum Hall is that you can think of it, it choose to be in that integer quantum Hall liquid state, and there's some residual charges because you're not at the exact filling factor of integer, and those extra charges, no matter if it's electron or hole, forms, for example, a trivial Wegener crystal that doesn't contribute to topology, and that is why it looks like integer quantum anomalous Hall effect, right? Maybe what we are getting here is sort of like an anomalous version of that integer quantum Hall liquid plus Wegener crystal. We cannot tell with a microscopic probe. Well, some local expert has visualized the Wegener crystals in quantum Hall case, right? Another possibility, okay, there's just more literature, and I just point out more differences. Usually, reentrant quantum Hall happens in high index lambda levels, and a relatively small range of filling factor instead of across the board from 1/2 to 1, right? And random quantum Hall is never seen in half filling. It doesn't get replaced, and there's no phase transition from random quantum Hall to fractional quantum Hall. There's another picture to think about what's going on here is this concept of Hall crystal first came up with by Bert Halperin in the case of the fractional quantum Hall at high magnetic field. So he's asking like whether you can break translational symmetry and the time versus symmetry. Okay, I guess in that case, time versus symmetry is broken by magnetic field anyway. But can these electrons break translational symmetry spontaneously, like in, for example, Wigner crystal? And several groups sort of borrow that thing and name it anomalous Hall crystal as maybe what's going on in this rhombohedral graphene HBN Moiré superlattice. And in that case, the crystal has to break both time versus symmetry and the translational symmetry at the same time, spontaneous fashion. So this is a new topological state. It's kind of the topological version of Wigner crystal, if you can think about it that way. And in this case, it doesn't really depend on Moiré, because the anomalous Hall crystal, forms the integer filling of a lattice of itself. So it can expand, it can shrink depending on the charge density, but it doesn't need to be commensurate with anything else. So that sort of matches our observation of this H over E square state residing, a region on the phase diagram that doesn't seem to be super relevant to Moiré filling factor 1. Okay. But again, in our case, we still have Moiré, right? You cannot just say, oh, Moiré is not doing anything, although it's there. So we still don't know what the Moiré does in this case. Maybe Moiré helps stabilizing this anomalous Hall crystal a little bit, although it's not super obvious. I mean, I can understand why Moiré stabilizes at the fractional fillings that's commensurate with Moiré, but if I'm picking up some weird fractions like 100 over 133, it's not super obvious that Moiré will help stabilize the anomalous Hall crystal there, right? So maybe the experiment that we really need to do ultimately is to completely get rid of the Moiré with large Swiss angle between graphene and HBN and ask if this integer quantized Hall state can still persist or not. Maybe this crystal can still be pinged by impurity or defect, just like Wigner crystal can be. Okay, but that is effort in future. So here I'd like to wrap up. I've shown you many topics happening in this rhombohedral graphene HBN. Rhombohedral graphene system proximatized by TMD by Moiré, and many phenomena doesn't rely on Moiré. Maybe even part of this doesn't rely on Moiré, but it has Moiré in there. So this is a very rich platform to study electron correlation and topology. And it's not even the end, because there are more things you can envision to be done here. Once you can get flat band at the 0 magnetic field, you can use that as a building block to build more things that have never been realized before. For example, you can possibly explore exciton condensate by making a double layer structure, like a pentalayer graphene, a thin HBN, and another pentalayer graphene. You put electrons in one of the pentalayer graphene, put holes in another pentalayer graphene, and they just spontaneously attract each other and form exciton condensate. That would be, and at the 0 magnetic field. This has been done in the double layer gallium arsenide quantum Hall system, but has not been realized in 0 magnetic field. So that could be one thing that we can explore. And of course, there are a lot of things to do in superconductivity, maybe combining with topology. And even for the fractional realm, there are so many open questions we don't understand. So this will be ongoing effort for quite some time. With that, I'd like to thank you for your attention.
8 minutes for questions. Could you talk about how you do twist angle alignment? Like, are you deciding to specifically have like a 0.55, angle degree offset between your HBN and your graphene, or are you just closely aligning them and then calibrating it essentially?
Okay, so we always look at a straight edge and try to align with the straight edge. And some devices will have moire, some do not have moire. For those have moire, the angle could be 0.5, could be 0.7. We don't have super accurate control of the angle. So it is pretty, crude at that level. But now, if we want to be more systematic, we probably should do a better job in determining the angle of the crystals and aligning them more precisely. But that hasn't been done yet. Yes.
So unless I think you can show magnetic field dependence for the extra quantum anomalous Hall range, and I'm wondering, you showed one example where strata and quantized value disagree with one another, and I'm wondering if you looked at that here.
Okay, so we did do the lambda fan in a bigger range, but the thing is, this thing is so broad, right? What you will see is that this whole broad range will shift, but the boundary of this region does not necessarily follow strata, because the boundary could be determined by something else, right? I think there is phase transition from this integer to fractional state, or the opposite, as I'm not sure which one we saw, but there could be magnetic field induced phase transition like that. Yeah.
So how is the temperature? Would you see this re-entrant state compared to the bandwidth of the flat band?
Ooh, I think we probably start to see this at like 100 millikelvin level, and that is 0.1 K, and 0.1 K is 10 micro millivolt, right? 8 microvolt, right? But this is an extremely small number. Yes.
In the devices that aren't aligned with or have a large twist angle, is there still an anomalous Hall signal, even if it's unquantized, or is it just?
There is an anomalous Hall signal, but it's not. It's far from being quantized. At least at the temperature we have checked. Yes.
Did you show the nonlinear IV data again?
Yes, or
the one versus current?
yes.
Yeah. So, I wonder if this reflects the pinning of the integer crystal. Have you looked for noise when you're in the high conductance region?
No, we have not, but we would love to do that. So I think Ray's student is now setting up to measure not this crystal, but the Wigner, because that persists to higher temperature. And eventually, I hope we can do that for the narrowband noise for this state and see if there's narrowband noise in there. But I agree with you that if you look at the IV or VI relation of Wigner crystal, and you plot it as a function of voltage instead of current, you also get this kind of depending thing. This really reminds you of that, except for this is versus current and that is versus voltage. But that could just be due to this swapping of the role of the current and voltage due to the Hall effect, right? But there are also experiments people have done on integer quantum Hall effect. I mean, Chern insulators, where they see breakdown of the Chern insulator state and shows kind of like peaks like this. So I cannot claim this is depending.
So in many phase diagrams you showed before, for example, this one, there appears to be a strong particle Hall asymmetry. For example, you have 2/3 filling, but not 1/3. It happens in more TNT material, and also here in multilayer graphene. Is there any reason behind this asymmetry?
I don't know. We never see one, not even at a high temperature. The 1/3 region is occupied by that very insulating state. Yeah, this whole region, I mean, it becomes even bigger if you go to lower temperature, and that sort of eats part of the fractional region at the bottom. But 1/3 was never showing. Yes.
More bands, right? How large or how small is that compared to this 14 millikelvins you're working at? Which is so different behavior sharing insulator.
Oh, you mean the gap between the first and the second Moray band?
Right. This should be very small, right?
Not necessarily if you include interactions.
Yeah, so you can include interactions. How small the gaps are.
I mean, some of the paper claim like even close to 1080.
I see.
Yeah. I don't know if you need that data. Yes.
And do you see potential to realize fractional topological insulators also in graphene systems?
Okay, fractional topological insulator. I think it was several steps from that. I mean, topological insulator is the first thing to look for. I actually don't even know what fractional topological insulator is.
In Hall effect. You have a Laplace and a Laplace conjugate that have intraspin mixing.
Okay, too far from where we are now. Because...
Maybe 1 or 2 more questions.
On the strong side of the devices, have you checked the temperature dependence there?
This is taken at an electronic temperature, we believe, between 300 millikelvin and probably 1 Kelvin. And they're sort of stuck there in this fridge because it's a helium-3 fridge. I haven't checked even lower temperature.
Just up to 1 Kelvin.
I have to check, but I think it hedges in millikelvin.
I have a question about how you make the samples. Do you intentionally grow them rhombohedral, or like naturally rhombohedral parts, you make your devices there?
Yeah, so basically you randomly exfoliate and you use this infrared microscopy to look for the region that's rhombohedral. And you have to cut it out from the rest of the flake in case the domain wall moves and kill the rhombohedral. And then you try to pick up the rhombohedral flake and with HBN to put it down. But starting from a rhombohedral flake doesn't mean you'll get a rhombohedral eventually, because HBN is super smooth and the rhombohedral is not the most stable stacking order. Most of the time, rhombohedral become Bernal.
If there are more questions, feel free to ask the speaker at lunch, but let's thank him again.